Hi class. For physics today, we're going to cover three common early introductory topics for Physics 1, which are going to be motion plots, common trig angles, and vector addition. When it comes to motion plots, this is similar to stuff that you're going to be working with in your early labs. We have positions like position versus time, or p as a function of t. We have velocity as a function of time, v of t, and we have acceleration as a function of time, a of t. Position in units of meters, velocity in meters per second, and acceleration in meters per second squared, and all of these are versus the time axis in seconds. Well, something cool about position versus time, the slopes of this plot equal the values for velocity versus time, and the slopes of a velocity versus time plot equals the values for acceleration. For our class, we're going to keep things a little bit simple and have line segments instead of curves. Breaking our position versus time plot into three regions, three line segments, slope A, B, and C. For any particular line segment, the slope is the final y position minus the first y position divided by the second x position minus the first x position. So for line segment A, that would be positive 5 meters minus 0 meters divided by 1 second minus 0 seconds. And that gets us positive 5 meters per second for a slope. For line segment B, that's a horizontal slope, so it's okay if you automatically just put that as 0. And the units meters per second are because we have position in meters divided by time in seconds. And for line segment C, well, the y positions are going to be negative 10, minus 5, and then 4 seconds minus 2 seconds for our plot. And that's going to give us a value of negative 7.5 meters per second. Interpreting our position versus time plot, essentially we have some object that is starting at the 0 mark, and for the first second, it's moving forward to the 5 position. And then from 1 to 2 seconds, it stands still, and from 2 to 4 seconds, it starts moving backwards until it reaches the negative 10 position. For a velocity versus time plot, just use the slopes of position versus time as your actual values for velocity versus time. So from 0 to 1 second, position versus time was positive 5. So for 0 to 1 second, we're going to fill in a value of positive 5. From 1 to 2 seconds, we had a 0 slope in our first plot. So for velocity versus time, from 1 to 2 seconds, it will be 0. So highlight that if it's on the x-axis so that's easier to see. And then from 2 to 4 seconds, our slope from our prior plot was negative 7.5. So we'll have that filled in for the entire region as 7.5. Common error for this type of stuff, when I start with one plot and ask my students to make a second plot, they sort of make it like a scatter plot, which is all jagged. Really, if you're starting with line segments in your first plot, then your next plot should look like a bar graph. And we're just going to connect all these different points just for aesthetics. And that's a good way of doing a velocity versus time plot if you're starting with position. And if we go from velocity to acceleration instead, then it's the exact same process. Most of your examples for velocity versus time are going to be sloped lines, like in our first plot. That way, acceleration is not just all 0. In this particular case, though, the slope of every point on our velocity versus time plot is a 0 slope. So that means that we're going to shade in a value of 0 for the entire 1 to 4 seconds. For our acceleration versus time plot, acceleration is just 0. And that's the basic process of how to take one plot and make the next. So you can use that technique for making predictions in lab on what one plot is going to look like if you're starting with a known plot. And yeah. Now, we're going to get into vector addition. There's some common angles that you're going to see a lot in this class, which is a angle or theta with a value of 30 degrees, 45 degrees, and 60 degrees. And our two common functions are going to be sine and cosine. Well, if you ever have sine of 30 degrees, that's the same thing as square root of 1 divided by 2. Sine of 45, you could substitute that with the fraction square root of 2 divided by 2. And then sine of 60 degrees, you can take the value square root of 3 times 1/2, or square root of 3 over 2. And that's the same thing as sine of 60 degrees. So the pattern is square root of 1, square root of 2, square root of 3, all times 1/2. Obviously, square root of 1 over 2 is just 1/2, so if you don't need the square root to remember the pattern, you can still just use 1/2 instead for sine of 30. For cosine, it's the opposite pattern. From cosine of 30, 40, and 60 degrees, that would be square root of 3 divided by 2, square root of 2 divided by 2, and square root of 1 divided by 2. And that's the pattern for when we're working with cosine. And again, square root of 1 divided by 2, that's just 1/2. So you don't need to draw the square root if you don't want to for square root of 1 over 2. In order to do vector addition, you must be adding parallel vectors. They have to be parallel with each other. And in this case, I have vectors that represent velocity, meters per second, velocity along the x-axis. When you draw a vector, like vector A, B, and C, the length of the arrow for that vector should correspond to the magnitude, and then the arrowhead should reflect the direction. So vector A has a magnitude of 5, so that's a pretty long arrow. It's positive 5, so the arrowhead is to the right. Vector B is negative 2. 2 is less than 5, so a slightly smaller arrow, and it's negative, so it's pointed to the left. Vector C is negative 1 meters per second. So the arrow for vector C is going to be smaller than vector B, because 1 is smaller than 2. And it's negative, so it's still pointing to the left. As long as all the vectors that you're adding together are parallel, then the resultants, A plus B or A plus B plus C, however many you're adding, is just adding your values together. So positive 5 plus negative 2 plus negative 1 will give us a value of positive 2. And then when we draw our resultant vector, R, positive just means to the right. 2 means that it's going to have the same length as vector B, because vector B was negative 2, but now the resultant is just in the opposite direction. If during lab you're asked to draw a 0 vector, that would be just a dot, instead of anything that's pointed to up, down, left, or right. On our xy axis, xy grid, if a vector is just on the y-axis, up means positive, down means negative. If a vector is just on the x-axis, right means positive, left means negative. Now, not every vector and most vectors you add together are not going to be parallel. So if we want the resultant of A and B, where vector A has a magnitude of 6 meters per second, and it's up and to the right, 30 degrees above the x-axis, and vector B is down and to the left, 60 degrees below the positive x-axis. Vector B has a magnitude of 18 meters per second. We're going to need to break these vectors into their x and y component. Now, since our vector is not on just the y or just the x-axis, we no longer have positive and negative for our directions. Instead, we have our angles. Our angles are going to be our direction information for our vectors. Now, to break a vector into its component vectors, start at the tail of your main vector and draw one of your components. For vector A, I'm starting with the x component. So from the tail of vector A, it's pointing to the right. So I'm going to draw just a vector that's to the right. That's AX. And now from that vector, from that component vector at its arrowhead, I'm going to draw the next component vector, which is AY. In this case, AY is pointed up. For vector B, just to show you that it doesn't matter which vector component you start with, in this case, from the tail of vector B, I'm going to draw the Y component, which is pointed down, and then from the arrowhead of BY, I'm going to draw the X component, BX, which is pointed to the right. So that's the key here. You draw one component, and then from that arrowhead, you draw the next. You don't just draw both of them at the origin. To break up vector A and B into its X and Y components, we're going to use trig functions. So for this reason, make sure you have your calculator set to degrees and not in radians. I have many students who are also taking calculus, and usually they're in radians for their Calc 2 or 3 class. Well, make sure you're in degrees for this part of our course for physics. For AX, or the X component of A, we need to take the original magnitude of A times cosine of our angle, 30 degrees, and I have a positive 1 here for direction. Since AX is pointed to the right, that's the positive X direction. So we have 6 times cosine of 30 degrees times positive 1. Cosine of 30 degrees, that's the same thing as square root of 3 over 2 if you want to do a substitution. Or you can just type this in your calculator. What you're going to end up getting is positive 3 square root of 3 meters per second. For the X component of B, BX, the only difference is we use the magnitude of B multiplied by cosine of the angle we're given, 60 degrees, and BX is to the right, so we'll also multiply that by positive 1. That becomes 18 times 1/2 times positive 1, or positive 9 meters per second. For AY and BY, what's going to change is our trig function is going to be sine for our Y component. So AY will equal A times sine of 30 degrees times positive 1, because AY is pointed up. That's why I'm using positive 1 here. That becomes 6 times 1/2 times positive 1, which equals positive 3 meters per second. For BY, that will be the magnitude of B times sine of 60 degrees, and then we're going to multiply by negative 1. The reason why I have negative 1 here is because the Y component of B is pointed down. If you have a component vector that's pointed down, then that Y value should be multiplied by negative 1, or it should be negative by the time that you finish and get an answer. If you have an X component that's pointed to the left, then that would be negative as well. The reason why I'm doing this, adding the +1 and -1, is because I'm not taking the angle starting from the positive x-axis, going counterclockwise all the way to the vector. If you plug that angle in your sine function, then it would automatically include the negative. Here I'm just keeping the angle between the positive x-axis to our main vector, 60 degrees. So instead of going this direction, I'm going this direction. That's why you got to make sure that if your answer should be negative and it's not, that you make sure it becomes negative through multiplication. Anyways, BY will equal 18 times square root of 3 over 2 times -1, or -9 square root of 3. If I had vector C, then it would just be the same process. We would have CX and CY. When you're all done, add up all your X components together, because those are now parallel, to get your resultant X component, RX. So AX plus BX will be 9 plus 3 square root of 3, which visually, to better understand that, that's about positive 14.2 meters per second. While I cut it short here in lecture, for an actual worksheet or for an exam or for your laboratory assignments, if you need to take an intermediate value and you're not going to use the whole value, like 9 plus 3 square root of 3, if you're going to shorten it to like 14.2, go out to like 5 decimal places and then use that value in a future calculation. Just making sure that we're still recording. Good. Now, for ry, the resultant's y component, add all your y components together. Ay plus by plus cy if we had a cy. That's going to be 3 minus 9 square root of 3, and that's approximately negative 12.6 meters per second. The last thing we're going to need to do with this bit of information is calculate our magnitude of our resultant vector, the direction, and then draw it or sketch it. For the magnitude, think of the equation ax plus bx equals, or a squared plus b squared equals c squared. Rearranging it, our resultant magnitude equals the square root of rx squared plus ry squared. Because rx or ry might be negative, make sure you put its value for rx and ry in parentheses, and then outside those parentheses put a square. That way it does not ignore the negative sign inside parentheses if it becomes a negative value. You want to make sure that that negative gets canceled out. So you could use a decimal version up to 5 decimals. I'm going to use the whole value. So I have r equals the square roots, and you could have a set of parentheses here if you're typing this into your calculator, and then a second set of parentheses, 9 plus 3 square root of 3. Outside of that parenthesis, have square, plus parenthesis 3 minus 9 square root of 3, parenthesis squared, and then have your other parentheses encapsulating everything if you're typing this into your calculator, and have the square root of the entire thing. This gives us a resultant r of 19 meters per second. As far as direction goes, we need to use the tangent function temporarily. Tangent of theta equals ry divided by rx. While rearranging that, your calculator might show it in two different ways. The more common way is showing the inverse tan function, tan to negative 1. I like to write it as arctangent, or arctan, of ry over rx. In either way, whichever way your calculator has it, click that button, write ry divided by rx, its values. In this case, I'm using the whole value for ry and rx, so theta equals arctangent, big parentheses, numerator, small parentheses, 3 minus 9 square root of 3, and then in the denominator, small parentheses, 9 plus 3 square root of 3. And that gives the whole as accurate as possible of a value, negative 41.58 degrees. For lecture, if you get an angle that's negative, just ignore the negative sign. We don't need it for our purposes because we're going to figure it out by sketching our component vectors, what the correct angle direction is. Just have 41.58 degrees. If you keep the negative sign, that's okay, I won't mark it wrong. If you leave it out, I'll still mark it right, 41.58 degrees. Now that we have our components of our resultant, its magnitude and angle direction, last thing is to sketch it or draw the resultant vector. On our XY grid, choose one of your component vectors and start at the origin. So I'm choosing Rx in this case. From the origin, I drew Rx. Rx was positive 14.2, so I'm going to draw that to the right because it's positive. And now, from the arrowhead of the first component vector you draw the second component vector. Ry came out as negative 12.6. Negative means down, so I'm going to draw Ry as down. 14 and 12 are about the same length, so that's why these arrow lengths are about the same. And now, in order to make sure it's correct, from the first component vector you drew, start drawing the tail of your main resultant vector, and then draw it toward the arrowhead of the second component vector you drew. A very common error I've seen is past classes, students might draw both component vectors with the tail at the origin and then connect the arrowheads. That's super wrong. Draw one of your component vectors, then draw the next component vector, and then From the tail of the first to the arrowhead, from the tail of the first component vector to the arrowhead of the second component vector, draw your resultant. And now, between the x-axis to whichever is closest to the vector, to the resultant vector arrow, I'm going to draw in theta r. I'm going to label my resultant as r. And if you don't have room in your plot, then off to the side, label r as 19 meters per second. And in theta r, the resultance angle, label that as a value of 41.58 degrees. Again, I'm not showing the negative sign just because per the component vectors, I already know the direction that I should draw theta, not up here, but down here. Yeah, that concludes our lesson for physics. Hope all of you are doing well. And for those of you who are not in my class, hey, if you would like to, you can like the video, leave a comment, and also subscribe to the channel. I like saying that because it makes the subscribe button look like a rainbow. At least it does right now. But in any case, wish you all the best. Glad to have you all in class or beyond. And peace.